But basically, we're going to look at some exponential function applications today. We'll look at some more applications, but right now we're a little bit limited with our tools that we have. Eventually, we'll learn about something called logarithms that will let us solve for different parts in these kind of general exponential equations. So eventually, we'll come back and revisit some other types of word problems. But exponential functions, they're used a lot of times, like I said, in biology, if you're trying to model like population growth of like some kind of animal or just people or whatever it might be. Or you can use it to kind of measure cell growth or the decay rate of different kinds of atoms or different types of elements. And also it's used a lot of times in finance to kind of calculate interest rates. We'll eventually learn some more kind of tools. There's different types of interest rates you can calculate. But right now we're kind of just looking at the basics. You might have seen questions, but our equations are always going to use this general form of our equation. We're going to have a times b up to the x power. Very similar to what we saw yesterday when we were graphing, except it's a little bit more simplified because we won't necessarily have as much going on. In general, when you're doing these types of problem, a in this formula is basically going to be your starting amount or how much you begin with, whether that's money, whether that's like your initial population. B is going to be your growth or decay rate. And one really important idea is when you're dealing with percentages. For example, if you have 100% of what you started with, you have the same thing. So for example, if I weighed 100% of what I weighed last year, I'm the same weight. If I weighed 90% of what I weighed last year, well, I lost a little bit of weight. If I weighed 110% of what I weighed last year, which is probably true, I definitely put on a little bit of weight during quarantine, I would be like 110% of what I weighed before. So kind of keep in mind when we're dealing with percentage questions, 100% is kind of like your base. That's like if you stayed the same, you have 100% of what you started with. And X is going to be your time, or more importantly, X is going to be how many times this is going to occur. So if you're decaying by 5% each year, like how many times is that decay going to occur? So looking at our first example, and these are coming straight from the delta mass section you'll be looking at. Like I said, you're using this y equals a times b to the x formula. You just kind of want to plug in what we have. Like, so if the town's population was 13,000, that's your initial amount. What it's growing by, this is your growth rate, but we'll see, this is going to help us find our b, but it's not actually our b yet. And then x is your time, or how many times it would happen. So if we kind of plug this into our formula, we're going to have 13,000 plugged in place of that a times, I'm going to wait to plug in my b, but up to the 11th power. So here's the deal with your b. Remember, you always start with 100%. So you want to ask yourself, is it growing or decaying? So since it's growing, we would add 5%. So basically each year we're going to have 105% of the population we had before. So our B is really 105%. When you plug this percentage into your formula, you want to make sure it's in decimal form. So if you don't know how to change like a percent to a decimal, just divide it by 100 or move your decimal place over to the left twice. But we would plug 1.05. That's 105% in decimal form. Because really what this formula is doing, if I wanted to figure out what 105% of something is, I could just multiply it by 1.05. And since we're doing, this is going to happen 11 times over 11 years, we're really just multiplying 13,000 times 1.05 11 times. But to get our final answer, we're just going to put this in our calculator. So 13,000 times 1.05 up to the 11th power. You get about 22,234.41166, but they ask us to round to the nearest whole number in this example. So that would just be 22,234 people if you want to put a label, but when you're doing the delta math, you're not going to have to put a label in your answer box. So let's look at another one. So another kind of example, you can use it to figure out how much something will be worth over time if you know its increasing or decreasing at a constant rate. Not always true necessarily, but you can use this to get a good estimate a lot of times. But you buy a new car for almost 20 grand, $19,900. That would be your initial price. The value of the car depreciates by 7.5%. What will the value be after 8 years? So depreciate means it's lowering in value. If you buy a brand new car, it's not going to be worth nearly what you paid for it 10 years down the road. So cars are not like a good investment to like make money, but obviously you need transportation. But no one's going out and buying a car and be like, yeah, I'm going to make so much money off this car. I mean, maybe if you're using it to make money, like Uber or something like that, it'll pay for itself. But a car is not like an investment for your future by any means. Like that, it's not going to appreciate in value. But if you plug this into your formula, you would just have 19,900 times, like I said, I'm going to find my B, but it's going to be up to the 8 years. So like I said, you always start with 100%. In this case, it depreciates, so you're going to subtract 7.5%. So that would be 92.5%. Basically, it'd be worth 92.5% of what it was each year. But you do want to put this in decimal form when you put this into your formula, unless the calculator you have has a percent button. Some calculators do, but like the graphing calculator, at least it's not. There's probably a percent somewhere under a menu, but it's not like at least easy to get to. But when you plug this in, you would do 0.925, or take your percent, divide by 100. But when you plug it into the formula, you want to make sure it's in decimal form. Like that is important. So we're just going to plug this in our calculator. If you read the directions, be carefully ask this to round to the nearest cent, especially since we're talking about money. So 19,900 times 0.925 up to the 8th power. It's roughly 10,665 and 0.64 if you round it to like the nearest cent. That would be dollars, but you don't have to put dollars when you're actually doing these in Delta Math. But you can see the car almost lost half its value in 8 years, which is very true. Like I said, if you buy a brand new car, it loses its value pretty quickly. I mean, not a bad thing to buy a new car, though. You won't have to pay for repairs and stuff. So there's advantages, obviously. Sorry, now my car is kind of not doing too well, but I'm just going to ride it till it dies kind of thing, and then think about that. So the second section you're going to see in Delta Math, it's called half-life and doubling time. You're going to be using one of these two formulas. It's very similar to the formula we were just using, except we're going to see with our x value or exponent, we have to be a little bit more thoughtful. But let's look at an example. So this first one, it says element X is a radioactive isotope such that every 25 years its mass decreases by half. Given that the initial mass of a sample of element X is 50 grams, so that's your initial amount, how much of the element will remain after 23 years? So in this section, you're either going to have something that's like halving each time, or it's going to double each time. So this one, it's like this radioactive isotope's decaying, so it's decreasing by 1/2. So we're going to use this formula. So if we kind of plug in, we know our A is 50. It was 50 grams to start. It's 1/2 on the inside, because if you think about it, that's really like 50% of what you started with. For our time, if you think about it, so this halves every 25 years, and we're only going to use, like, we only have 23 years we're looking at. So it's not even this half is not even going to happen one time. We really only have 23 years out of the 25 years it takes. So in this formula, the T is your time, and the H, I think they call it the halving rate. Basically, how long does it take to decrease the half of what you started with? So we only have 23 years out of the 25 years it takes to make half. So once you're here, though, you would just plug it in. They do ask us to round to the nearest whole number, so pay attention to that when you're doing this section, so you don't miss it if you don't round it to what you want. When you put this in your calculator, I'm just going to erase this so it's a little bit neater. you either want to figure out what this is as a decimal, or when you plug this in, put this in parentheses when you put that up to a power. Like that is important. If you don't put the parentheses, you could easily get the wrong answer, or you could turn it into decimal form, but especially if it doesn't work out nicely. But when I plug this in, I got 26.425, so that's closest to 26. So you'd have roughly 26 grams, which makes sense because it takes 25 years to be half of what you started with. So since we only have 23 years, it's going to be close, but not quite half. So that answer seems pretty reasonable based on the information. For this next example, we have a person that's investing money into an account that allows the money to double every 12 years. How much money would be in the account after 15 years? So since this one is doubling, obviously we're going to be using the double formula. So your A is the 1,500. That's how much money you start with in this account. So it's doubling. So that's our growth rate inside. Our time is we're going to invest it for 15 years, but it takes 12 years to double. So we'd really have 15 out of 12 years. It's going to double a little bit more than once, like not quite double twice, but between 1 and 2, because 15 over 12 is like 1.25, right? But you'll just plug this in. Like I said, when you put this power, if you're keeping it in fraction form, make sure you put parentheses around it. That's a key thing, where if you're missing these, that might be probably why. It does say round to the nearest dollar. So I got 3,567.62. So that would actually round up to $3,568. Let me know. Let me double check the chat. I haven't seen anything going on right now. Okay. And then, so honestly, like section 1 and section 2 in these notes, these are like the 2 sections you're going to see in your Delta Math. But I did just want to show you, like, I couldn't find any problems like these in Delta Math, but you could easily see a problem like this. Like, for example, maybe what you're looking at is tripling or quadrupling or something like that. But this problem, it says a biologist was conducting an experiment with a particular type of bacteria. She discovered that the bacteria reproduced at an alarming rate. It tripled every 30 minutes. And they tell us we start with 4 bacteria. How many would there be after 4 hours? So our A is 4. That's how much bacteria we start with. Our B, our growth rate, if it's tripling, is 3. Like, I mean, because that's like 300% of what you started with, if you want to think about it in percents. But basically, if it triples, your B would be 2. If it doubled, it would be 2. If it quadrupled, that would be 4. If it was half of what you started with, it would be 0.5. If it was a quarter, it'd be 0.25 kind of thing for your B. But here's where we got to be careful with a problem like this. Your X is your time, but really it's not just your, like, you don't want to just put 30 minutes or wait 4 hours, because that's how long we're looking at it. When you find your time, you really are thinking about how many times is this going to happen? How many times is it going to triple? So if it triples every 30 minutes and you're looking at this bacteria for 4 hours, you really need to figure out how many times would 30 minutes happen in 4 hours. So, I mean, one way you could do it, I mean, is just kind of count it on your fingers. Just think about it. Like, there's 2 half hours in an hour. So in 4 hours, there would be 8. Like, if you just could kind of see it. Or you can always just get a like unit. Like, 4 hours is really 240 minutes. And then you could just take 240 divided by 30. So, I mean, that's like the proper way to do it. But a lot of times you can kind of just reason it out or kind of see it. But your X would be 8, because that's how many times it would happen. And that's really what we're doing in this formula here. Like, that's why we have a fraction. This is really how many times would it double, or sorry, how many times would it be half? And this is really how many times would it double? Like, you're not going to have a solid rate. But then when you get it, you would just plug it into this formula. So 4 times 3 up to the 8th power. And you'll see a lot of times with problems like these, your answers get quite big because they're growing exponentially. But this would be 26,244. So you're not going to see any problems like section 3, but I just wanted to kind of show you a problem like that, because you could very well see like something similar to the problems in this. So I posted the delta